Here we consider design of a single shoe brake. For a single shoe brake, determine the normal reaction on the shoe. Normal reaction is denoted by Fn. Find the tangential force. Tangential force is denoted by Ft, and Ft is related to Fn by Ft equal to mu Fn. Diameter equal to 600 mm. Rotation is clockwise, so drum rotates clockwise direction. We are asked to find the effort required to operate the brake. Power equal to 10 kilowatts at 1000 rpm. So power and rpm is given, so we can find the torque. Coefficient of friction mu equal to 0.3. Angle of contact equal to 40 degrees. Also find dimensions of the brake shoe taking the bearing pressure as 0.05 Newton per mm square. So this is our question, and also the figure is also given. So we will analyze how the forces are acting and how the rotation is occurring inside the drum. Here it is given the drum is rotating in clockwise direction. Further, angle of contact 2 theta is given as 40 degrees. First we have to find what is the normal force and the tangential force. To find the normal force, we have the equation. Normal force equal to torque equal to 1 by 2 ftd equal to 1 by 2 mu fnd, where T is the torque transmitted. T is the torque transmitted. How to get the torque? We are given the power and the RPM. So first we will find what is the power, what is the RPM, and from that we can get the torque. So our equation for torque is 60 P by 2 pi n, where power should be substituted in Newton millimeter per second. So 10 kilowatts, so 10 into 10 power 6 Newton millimeter per second. Speed n equal to 1000 rpm. We will get torque transmitted equal to 95 to 10 power 3 Newton millimeter. Then I can go to this equation. Here mu is given, mu equal to 0.3. D is the diameter of the brake drum. Diameter of the brake drum is given as 600 mm. Diameter of the brake drum is given as 600 mm. Substituting all these values, I can get the value of normal reaction. Fn equal to Qt by mu d. We will get that value equal to 1061 newtons. Then we can find Ft. Ft is the tangential force. Ft equal to mu Fn. Ft equal to mu Fn equal to 300, mu equal to 0.3 multiplied by 1061, that is Fn. We'll get that value equal to 318.3 newtons. So I got the value of Fn and Ft. Now we have to find the effort required at the end of the lever. So effort required is the load to be applied at the end of the lever. In this section, we have to see how the forces are acting on the drum. Recollect the force analysis on the drum and the shoe. So here we have the drum rotating in clockwise direction. The drum is rotating in clockwise direction. I am drawing the free body diagram, so I am separating the shoe with the lever from the drum. When we apply, here we have the fulcrum. Okay. When we apply force P, the shoe will move downwards, or it will exert a downward force, that is the normal force Fn. Drum is rotating clockwise direction, so the friction force should be opposite to motion, that is Ft opposite to motion, on the same point on the shoe, Fn will be acting upward direction and Ft will be acting towards right. So if I know the value of Fn and Ft, I can get the value of P. So now we will present all the forces acting on the shoe, because we are interested in design of the lever with the shoe. So here we have the shoe. The force exerted by drum on the shoe will be acting upwards, Fn. Similarly, the drum is rotating clockwise direction, so friction force or the tangential force on the shoe will be in the direction of rotation, Ft. I have to get the value of P. What should we do? We have to take the moment about the fulcrum. Take the moment about this fulcrum point. I can mark it as fulcrum point as O. So taking the moment about the fulcrum, I can write P multiplied by P multiplied by 800. That's the distance between P and the point O. This is the point for O and P is the line of action. So P into 800, it is clockwise. Then if I look this figure, there are no other clockwise forces equal to sum of all anti-clockwise forces. First we consider Fn. Fn multiplied by 400, it is anti-clockwise. Similarly Ft. Ft is also anti-clockwise, plus Ft into 150. Again substitute the value of Fn and Ft. Fn equal to 1061 Newton, Ft was equal to 318.3 Newton. I will get the value of P. P equal to, find the effort required, that is a P equal to 590.1 newtons. Further, I want to design the lever. I want to find the cross-section dimensions of the lever, for which I will be using the moment equation. So we will see how it acts. So for the design of the lever, I know that the load P is acting at the end. So the lever is long, so it will have a bending in this direction. It will bend about this point. So I need to find what is the distance between line of action of P and this point X. So I know that this is a R radius. This angle is theta. Theta equal to 20 degrees. So this length will be R sin 20. So total length up to here is 400. So X will be equal to 400 minus R sin 20. This length is R sin 20. These two lengths remain same. So if I get the value of X, I can find the value P. P equal to moment equal to P into X. So that moment will be equal to P is equal to 590.1 multiplied by X. That value will be about 297.3 mm. 297.3 mm. Substituting the values, I will get moment equal to 175.46 into 10 power 3 Newton millimeter. So aim is to find the cross-sectional dimensions of the lever. Usually the lever will be made of steel and having a rectangular cross section. So our basic moment equation is sigma equal to m by z. So this is our moment m. Our basic equation is sigma equal to m by z. If material is not given, assume C40 as a material. From page 464, table 1.8, you have to by heart these page numbers. Sigma y equal to 324 Newton per millimeter square. And for rectangular section, Z equal to BD square by 6. Since now factor of safety is given, I will take that sigma equal to sigma y. So 324 equal to moment was found was 175.46 into 10 power 3 divided by BD square by 6. Here both breadth and depth are unknown, and since depth should be higher for reducing the stress, so I will take depth as a higher value, depth equal to 2 times B. So I will substitute that value, BD square by 6. From this equation I will get value B and D. Substitute D equal to 2B, I will get B equal to 9.33 mm and depth equal to 18.66 mm. Now we are moving to the last step of the design, that is the design of the shoe. Very simple step. So required area of the brake shoe ABS can be found from equation 13.16g. ABS represent area of the brake shoe. BS stands for brake shoe. Is the projected area normal to the direction of Fn, and P is the allowable specific pressure, mega Newton per meter square. In our question, P is given as 0.05 Newton per millimeter square. So pressure is known. Fn is also known. Fn equal to 1061 Newton. So I can find the area of the brake shoe, projected area of the brake shoe. Why we have to select a projected area? When we have a surface and the force is acting normal, having an area A, pressure equal to force per area. However, if the force is acting on a projected surface, on a curved surface, I have to take the projected area. So when we consider the projected area, I should see the top view. In such a case, the top view of a curved surface, I am looking from top, this will be the top view. I have to take this area. So this area will be A dash. So pressure for curved surface equal to force by A dash, where A dash is the projected area. This is the same case in our question also. Here our normal force is Fn, which is acting on a curved surface. The shoe is having a curved surface. So pressure equal to, for area equal to, area ABS equal to Fn by P, area will be this projected area, ABS, area of the brake shoe. Here this angle is theta, so this R sin 20, theta was given as 20 degrees, R sin 20, so this total length will be equal to 2R sin 20. This width is W, so this W is unknown, so I can substitute in the equation. ABS equal to Fn by P Fn equal to 1061 Newton. P is given as 0.05 Newton per millimeter square, and ABS is the shaded area, and shaded area will be equal to W into 2R sin 20, from which I will get the value of W. I will get W equal to 103.405. Now there is an addition to this lecture. Whenever the angle of contact between the drum and the shoe is greater than 60 degrees, so consider a case in which there is a brake shoe, 2 theta, from here we have the force. Whenever 2 theta, angle of total angle of contact, is greater than 60 degrees, I have to consider it as a long shoe. In such case, I have to substitute mu by mu dash, or replace mu to mu dash. How to get mu dash is given in this equation, 13.16 m, page 266. Mu dash equal to 4 mu sin theta by 2 theta plus sin 2 theta. For example, if angle of contact equal to 70 degrees, if angle of contact equal to 70 degrees, this is our equation. 2 theta equal to 70 degrees, mu dash will be equal to mu into 4 sin theta will be equal to 35 degrees divided by 2 theta. 2 theta will be 70 degrees in radians, 70 into pi by 180 plus sin 2 theta. So we can find mu dash, which will be slightly greater than mu, and we have to substitute that value in all these equations. Now, so in today's lecture we have studied how to design a single shoe brake. We can find the value of Fn, that is a normal force. Ft is the tangential force. Ft is related to Fn by Ft equal to mu Fn. So Ft equal to mu Fn. Whenever angle of contact is greater than 60 degrees, I have to replace mu by mu dash. Now we consider an anti-clockwise rotation of the drum also. Consider, suppose we have the drum here, the shoe is fixed on a lever, here we have the fulcrum. In such a case, we are interested in the design of the shoe. When we apply force in the upward direction, to apply the braking force, the shoe will be exerting a normal force in the downward direction. This is the normal force Fn. If the rotation is counterclockwise, it is easy to understand that the frictional force on the, or the tangential force on the shoe will be in the direction of rotation. If you consider another case, here we have the fulcrum, force P. If the rotation is clockwise, normal force remains same, normal force will be downwards. So normal force will be pointing from the center of the drum to the point of contact. Now, so I have fixed the value, fix the direction of Fn. Ft will be in the direction of rotation on the shoe, so Ft will be towards left side in this case. So this completes the design of the single shoe brake. Have a great day. Thank you.